Welcome to my 18 electron rule practicing tutorial series. This is the very first recording. Today is December 22nd, and I'm going to go through a whole bunch of examples from the current literature. So we have real examples of stuff that's been published, and we're going to count electrons and practice that for our exams. So I go to either inorganic chemistry or organometallics, which are American Chemical Society journals, and I scroll through the graphical content until I find something that looks interesting to me, and then I just snip it, like this one. I found that yesterday, and today I'm making the recording. So down here is the reference, and so let's zoom in and look at that. So we're going to use the neutral method, all right? And so if your professor is anything like me, and I give you this on an exam, and you write 18 electrons, I will give you 0 out of 10 points because you are just stepping in the dark and you're not proving it. So for me, you have to actually show the electron contribution of each contact, including the transition metal in the center. Because we are using the neutral method here, we are going to use all of the valence electrons, regardless of that this possibly is an iron 2 complex, or it's a neutral iron, or it's iron 3, we don't know. We don't have to determine that with the neutral rule. So we're going to use the s electrons and the d electrons. There's 6 d electrons and 2 s electrons, which is a total of 8 for iron. So we're going to use 8 electrons for that. Now I'm going to look at each contact, but I can save myself some time because the alloxacine ligand here, which is what this rigid fused ring system is here. So it's just a plain rigid disc that's coordinated here, and this is probably also why it has trouble not latching on with that one that's so far away. But that's beside the point here, right? So I'm going to use each contact, but I can save myself some time because I can just use this times 2 once I've determined the contact. I want to be careful though that they are the same and they are identical. This is a copy-paste job here. So this first one here is just like an amine. It's a nitrogen with 3 bonds away from the donor bond here. And so this is simply the neutral lone pair that is donating. So this is an amine type ligand. It contributes 2 electrons. Moving over to the second nitrogen that's attached to the iron. Now one of the bonds has disappeared, so 2 electrons are gone, or are they, or whatnot? Well, this means simply that this is a monoanionic amide type ligand. So we've got a lone pair here and a negative charge, and so we've got a monoanionic contact here. So that is a 1 electron donor. As I said, the other nitrogen of this ligand isn't making contact or donating any kind of electrons. They are arguing here that there's some sort of hydrogen bond interaction. Let's just ignore that for now and then look at it maybe a little closer just for fun. So now we have the aqua ligand left, and that one is just also, first of all, we have double of that, which gives us already 8 plus 6 is 14, so we're missing 4. So we most likely have a 2 electron donor for each of the aqua ligands, and yes, it's a neutral water molecule called the aqua ligand. Each contact is 2 electrons. We have 2 of them, and so we end up with a total of 18 electrons, which is a good prediction. So you were right, but you got 0 out of 10, and now having all this detailed information, you get 10 out of 10. I do want to look at the paper a little deeper, so I dug and I looked at it. This is the alloxacine ligand here. They abbreviate it as all L and then H. So they're looking at that H here. And so I'm going to tell you that a strong base will deprotonate that. And then this is how you can get the monoanionic contact that we see here, right? So, here really this hydrogen has been removed. But let's take a look at this one here, right? So this is the same thing, but the aqua ligands have been replaced with the chloro ligands, okay? And the hydrogen here on the N1 position is firmly attached. So this is no longer a monoanionic ligand here, right? So what changes is, of course, see here we still have 1, 2, 3. So this is an amine 2 electron donor, and that's an amine 2 electron donor. So now we have 1, 2, 3, 4 contacts that are amines. First, of course, we have the iron. Iron is 8 as before. Then we have the 4 amine contacts. And then instead of having neutral aqua ligands, which contribute 2 electrons each, now we have the chloro ligand, which is monoanionic. So each contact is 2 electrons. And this is how we end up again with 18 electrons. So this should give you an A on the exam. But I do want to go a little further and take a look at these. These are really 2 different types of ligands. The one shown here is a neutral ligand, right? And so the other one is monoanionic, okay? And so this really makes a lot of sense for the 18 electron rule. This is very rigid. We have trigonal planar contacts here, so this is really a flat, rigid disk. But there is a little bit of curiosity for the monoanionic ligand here, right? So they are actually calling this the isoalloxacine. And in base, you do get the protonation of this comes off here, and this is how you get your monoanionic contact. And if you remember, I drew in a lone pair here, and so that pair of electrons is still there. It's available because if you draw the detached ligand, you actually have 4 electrons here. This is monoanionic. And so one of these lone pairs makes the single bond, but there's always the possibility of making a pi bond here and donating 2 electrons to an empty d orbital of iron. And so you can do that twice, and you could get to 18 electrons this way. And then the question is, do we have a 22 electron species here, or do we need to take a closer look at how large these distances are? Unfortunately, they do have a crystal structure, but they do not have the distance between oxygen and iron from the aqua bond. They do have this distance here because they really are trying to say that there is an interaction between that nitrogen here and the aqua ligand. But that's that distance. But we don't know this distance, and they didn't provide it. But that's really just something interesting to look at. And so if you do look at the center here, the nitrogen center, the geometry, it sure looks trigonal planar to me. Again, I don't have the angle sum, which would tell us a little bit more, but it does look flat, and so that does indicate that there possibly are electrons that are being donated either this way or back to the ring. But I'll just leave this out there for you to think about. Maybe you can figure it out. Maybe you can put something in the comments and explain it to me or argue with me, and or dig out the crystal structure and the data for me. And so the next time we're going to look at some bridging ligands. It's enough for today. Come back next week for looking at this cool thing.